universe caused its particles to vibrate, so fast that the liquid had no stickiness, did over 13 billion years ago. Despite the universe being a perfect liquid, it was in turmoil. It was full of subatomic particles that smashed into each other, releasing more and more energy. Eventually, there was so much energy that unless the particles slowed down, they would never be able to bond and create atoms, the building blocks of matter. A universe like this would not be able to create the galaxies and stars, let alone us. At this stage, the universe had expanded to 8 times the size of the solar system, and it was still just 1/1,000,000th of a second old. But after the incredible turmoil of this first microsecond, the universe became relatively calm. Over the next 3 minutes, the expanding cosmos cooled sufficiently for protons and neutrons to bind together and form the first atomic nuclei, hydrogen and helium. These were not yet proper atoms. They were still missing a vital ingredient, the electron. In the hot, baby universe, there were plenty of electrons around, but because there was still so much heat and energy, the electrons were moving too fast to form bonds. It would stay this way for more than 300,000 years. 380,000 years after the Big Bang, the universe had expanded to the size of the Milky Way. It had now cooled from billions of degrees Celsius to a few thousand. And as it cooled, the electrons slowed down. The universe was finally ready to make its first true atoms. One of the scientists who discovered this critical moment in the history of the universe was Arno Penzias. In 1963, 30-year-old Penzias and his 27-year-old colleague, Robert Wilson, began work on a new antenna in New Jersey. Initially, they were studying cosmic radio waves, but they would soon stumble upon one of the greatest discoveries of all time. As they started to test their equipment, they detected an unexpected background noise.
It was additional signal, and it appeared to be coming from the sky. We eliminated very carefully the ground, even the solar system, because we did this winter to summer, seasonal variation, man-made sources of equipment. All these things were eliminated.
The two scientists began to wonder if the strange signal might have another, more earthly origin. They discovered there were pigeons roosting in the antenna, and it was covered with droppings. To find out if the pigeons were in fact the source of the strange signal, they would need to get rid of the droppings and the birds.
We finally got around to removing the pigeon droppings. We also had to remove the pigeons. That was a difficult problem because they turned out to want to come back, and we mailed them off to another site.
But even with the troublesome pigeons gone, the mysterious signal did not disappear.
And so we were left with the almost inescapable conclusion that this radiation was coming from the sky. I could not account for it.
The strange signal detected by Penzias and Wilson would turn out to be one of the most important scientific discoveries of all time. And the explanation for their mystery noise starts not with sound, but with the birth of light. These days, we take light for granted. But 13 billion years ago, the universe was opaque and dark. Light was trapped inside a thick fog of fast-moving electrons. But as the universe expanded and cooled, the electrons slowed down. Protons were then able to bond with these calmer electrons to form the first complete atoms of hydrogen and helium. The universe was now much less crowded with electrons, and light was released. It hurtled out across space in a blinding burst.
Had we been there, we would have suddenly seen this opaque universe become transparent. Suddenly the fog would lift and we would see a flash of light coming from everywhere around us. It must have been a spectacular moment.
Over time, this burst of light dimmed and cooled and became microwave radiation. It was this faint 13 billion-year-old microwave signal that Penzias and Wilson picked up on their antenna. What they heard was the quiet echo of the moment the universe formed the first atoms.
It's really the light from the origin of the universe. If you have an old FM receiver, if you tune between channels, turn the knob, and it doesn't capture it and pop to a station, you get to a part where there's none, you hear a... That's what we call noise. If you have a good radio set, 0.5% of that is actually the sound of the Big Bang.
We can also hear this moment on a television set. If a TV isn't tuned in to a station, a tiny fraction of the noise it emits is radiation from 13 billion years ago. But this radiation is not the only reminder of the birth of the universe. Even the water we drink is a memento.
And it's kind of amazing to think that every time we take a drink of a glass of water, we're drinking in atoms that have been around since the Big Bang, the hydrogen atoms.
Over the next few million years, the young universe continued to expand, cool, and get dark again. So far, the universe had only made hydrogen and helium atoms. But the world we live in today is made up of more than 100 different elements. Without them, the universe would have remained gaseous, a place where complex matter like planets, cars, and people could never develop. The universe needed to get its hydrogen and helium atoms to fuse. And to do that, it needed to make stars. By the time the universe was 200 million years old, it was billions of light years across. Its temperature had dropped so much that it was colder than liquid nitrogen, minus 220 degrees Celsius. It was also dark, and it might have remained in this gloomy state if it hadn't been for one thing. The baby universe wasn't born perfect. Carlos Frenk has created an amazing 3D simulation of how the early universe evolved. It shows that when the universe emerged from the Big Bang, it was uneven.
Little cracks appeared, which were very, very, very tiny, very, very small. And it was this rash in the face of the baby universe that later developed into the patterns that we see in the galaxies today.
Without these cracks, the universe would have been a far less interesting place. The first clues as to how these cracks developed into galaxies and stars came when other scientists began to examine the Big Bang radiation first discovered by Penzias and Wilson.
So what Penzias and Wilson saw was this radiation was, as far as they can tell, uniform. What cosmologists then did for the next 25 years was work very hard to try to find tiny variations.
They found them using WMAP, a space probe designed to detect and analyze in detail variations in the background microwave radiation. Launched in 2001, the $150 million probe was fitted with some of the most sensitive instruments ever carried into space. Our eyes can detect only visible starlight, but WMAP can tune into invisible microwave radiation. Once in orbit around the Sun, it picked up the faint radiation that had been rippling around the universe since the dawn of time.
So when we look at the clusters of galaxies and superclusters and galaxies themselves, these low-density regions, these will grow and become the empty regions between galaxies. So this picture really is our connection between the universe when it was a baby, 500,000 years old, to the universe today, 13.7 billion years old.
These tiny imperfections in the fledgling universe would eventually become galaxies and stars.
And this is one of the most amazing propositions in physics. The idea that galaxies like a Milky Way that contain 100 million stars once began life as a tiny little crack in the fabric of the universe.
The material in these cracks was filled with swirling clouds of hydrogen atoms.